All right, we're going to do a simple model here. We have a car skidding, so the wheels are locked, and so we have friction due to the wheels, and it skids into the wall. We're going to call our zero position the point where the bumper engages with the wall, and we have mass, damping, and our spring constant here. All right, and their initial conditions. So we'll start measuring the moment it hits the wall. That'll be our 0 point. But the velocity, we're going to have our initial velocity of the car be 3 meters per second. So contact at t equals 0, bumper stops immediately, wall doesn't give, and we have the velocity as we come into the wall. So to model this, it's very straightforward. As we move this mass ahead, we're going to have relative to the ground minus bx dot opposing, and then minus kx opposing the motion. And we can bring all of this to the other side. And here's our initial condition. Xm of 0 is 0, and our initial velocity is 3. All right? So if we substitute in here for mass, damping, and spring constant, we'd have this. This is a homogeneous differential equation. I'll divide through by 750. That leaves me with this homogeneous equation, which is a lot nicer numbers to play with. I then take this to MATLAB. So I look at the characteristic equation, and I find that the roots are at minus 2.5 plus or minus 4.33i. Okay, so if we, given this, we can then just use our complementary solution and say the xm of t of the car is e to the minus 2.5t, the real part. And then the complex part will give me an a cosine 4.33t. So here's the complex, the omega d, and b sine of 4.33t. And I have two elements to figure out. All right, x of 0 equals 0. You let this be 0, that becomes a 1. Cosine of 4.33 times 0 is cosine of 0, which is a 1. Sine of 0 is 0. And so we're left with 0 equals a. Wipes out the whole cosine term. All right. You take the derivative of this. Set time equal to 0. I'll let you check this out, but you'll have a minus 2.5 e to the minus 2.5, well, e to the 0, so a 1, times b sine of 4.33t. But you let t be 0, sine is 0, so this term goes out. Right? Now you take the derivative of this term. This becomes e to the 0, that's a 1. So you're left with 4.33 times b cosine of 4.33, where t is 0. That becomes a 1. So here's what you have. 3 times 4.33b, or 3 equals 4.33b. Solve for b, you get 0.693. Substitute in. Here's our equation of motion. Xm of t is 0.693 e to the minus, oops, this is an error, e to the minus 2.5t. Sine of 4.33t, there we go. If you wanted to get the spring force, you take x, multiply by the spring constant. Boom, there it is. Now again, how long is this equation good for? All right, we start measuring the moment that the bumper hits the wall. That's x of 0. It goes in and it comes back. When it gets back to 0 again, as the car goes a little bit further back and goes negative, the bumper will disengage. It's no longer a valid set of equations. So let's look at that from this point of view. What makes it go in and come back? That's the sinusoid. So at time equals 0, sine of 0 is 0. When 4.33t equals pi, you'll be back to sine of, for whatever t, it's 0 again. So when 4.33t equals pi, solve for t at 0.73 seconds. We're at sine of pi, which is 0. That's when the bumper, at the next moment, disengages from the wall. The equations are no longer valid. So there's our analysis. And it's all finished. I have one more page of problems to consider. Also use